Hello grade 10s, today we're going to look at some past paper practice for physical sciences chemistry, and in particular we're going to be focusing on the kinetic molecular theory and heating curves. You can see here that I got these papers, National Senior Certificate papers from the Department of Basic Education, and they are papers ranging from around November 2018 back down to November 2016. Now, if you missed my previous video where I went over the theory of the kinetic molecular theory and also a video on the heating curve, please watch those videos first because I'm not going to re-explain the theory from scratch. We're just going to answer past paper questions. I will speak about the theory and why I'm choosing certain answers, but if you really need help with this topic, go back and watch those videos. Right, we're kicking it off with a multiple choice question, which you know in physical sciences is always question 1. All the way from grade 10 up to matric, you're going to get multiple choice questions, and they can be more tricky than you think. So this one says the graph below shows the heating curve of a substance. We know it's the heating curve of a substance. We don't know what substance, but we know it's the heating curve because we've got temperature here on the y-axis and time over here on the x-axis. As time goes on, we are adding heat to the substance and it's causing temperature changes in some cases. So it says in which part or parts of the graph does the substance gain kinetic energy? Now remember, gaining kinetic energy is directly related to an increase in temperature. When an object's kinetic energy increases, the particle's average kinetic energy increases, and average kinetic energy is a measure of temperature. Average kinetic energy is a measure of temperature of a substance. So when a substance gains kinetic energy, it's basically when the substance is increasing in temperature, and we can see the only part of the graph where we see an increase in temperature is from B to C. So your answer is A. Here we've got a past paper that looks at two substances, the heating curve of two substances. And I know it's a bit blurry, I'm going to make this a bit bigger in a second, but again we've got temperature on our y-axis, time on our x-axis, and we've got a dotted line and a solid line to represent the two different substances, and they ask us a whole bunch of questions on this. Now remember, always read the little paragraph before, just in case they give me any extra information, which they don't really. So let's take a closer look at these curves. Now you'll recall from my previous video on the heating curve that the flat part of the graph is where a phase change is taking place. So for example, melting, right? So a solid going to a liquid, or a liquid going to a gas, boiling or evaporation. So those are the flat parts. The inclined part is when the substance is in one phase and the temperature is just increasing, the kinetic energy is increasing. So here we can see basically that at 0 degrees Celsius, you can see over there, at 0 degrees Celsius, it appears as if substance 1 is going through a phase change. From this point over here to 0 degrees, it was most likely a solid. This is a phase change. Over here from 0, so 10 seconds where it's at 0 degrees, to 20 seconds where it is at 100 degrees, it looks like it's in its liquid phase. And just based on these numbers, so a melting point at 0, a boiling point at 100, that looks like substance 1 is water. I hope you guys can see that. And I just made that assumption based on the melting point and the boiling point. So again, remember the melting point is the first flat part of the graph, because the flat parts, the horizontal parts, are where phase changes take place. So this will be melting. So if they ask for the phase change, you say melting. If they say from what phase to what phase is it going to, it's going from solid to liquid, and the phase is present when a substance is melting is solid and liquid. So just watch the previous video if you're not too certain about what I'm talking about. Then we've got a liquid phase, then this is boiling or evaporation. That is the phase change. But the phases present would be liquid plus gas phase. And then this would be the object in its gas phase, or the water, H2O, in its gas phase. Then we've got substance number 2, which is represented by the dotted line, and we can see over here, there's the flat part of the graph. The melting point of substance 2 is lower. Okay, over here again, this flat part of the graph represents the boiling point, the phase change, boiling or evaporation. It's much lower than substance 1. But let's jump into the questions. 3.1 asks a very typical question for you to see in almost every science exam. Something along the lines of an experiment, something along the lines of an investigation. They are going to ask you dependent variable, independent variable, control variable, hypothesis, investigative question, conclusion. So you need to make sure you understand the scientific method in terms of physical sciences. So in this question, they want you to write down the dependent variable and then the independent variable. So now, a nice way that I remember it is the dependent variable is always the one that you measure. It is the one that depends on the other variable. Dependent, it's in the name. Dependent. It depends on the independent variable. So we change the independent variable, and that in turn causes the dependent variable to change, and we measure that change. So in this graph, it's very clear that the variable that we measure is temperature. So my dependent variable would be temperature in degrees Celsius. Again, because we are mentioning a variable, please mention the unit in which it is measured. Another nice way to remember dependent versus independent, if they give you a graph, is if I have to draw this graph for you like that, the dependent variable, dependent, goes on the y-axis. The independent, I hope you see what I'm doing there. The independent goes on the x-axis. Then the independent variable in this experiment, remember the independent variable is here, it's on my x-axis, that would be time in minutes. And time is basically also as heat is added, okay? So then they want an investigative question, and I'm going to show you exactly what the memo's answer is for this, and we're just going to discuss a very important part, one very important point when it comes to investigative questions. Now you can see that the memo says, what is the relationship between an increase in temperature over a period of time and phase change? There's two very important things that I want you to take note of when it comes to an investigative question. Three things actually. The first thing is I always want you to start your investigative question with what is the relationship between? Always. Then I want you to always mention both variables. So what is the relationship between the dependent variable, so you fill in whatever your dependent variable is, and then you fill in the independent variable, and you must put a question mark. If you don't put a question mark, they're going to take marks off because it's an investigative question. It makes sense. The reason we start with what is the relationship between, that is because we don't want your question to be answered with a yes or a no. So you can't say, as time goes on, will temperature increase? That is not a good investigative question because I can answer that question with a yes or no, and there's no further clarification or explanation of the relationship between the variables. So just remember, an investigative question is going to prompt a hypothesis, a conclusion. It basically links your two variables. You want to investigate the relationship between those two variables. So if you say, as time goes on, does temperature increase in phase change? I can say yes. So I can answer yes to that question. That is not explaining the relationships. But so by starting your investigative question with what is the relationship, you cannot answer this with a yes or a no. You have to explain the relationship, and that's exactly what we want. So here, just take note that they do mention both variables, and they do throw in their phase change because as time is going on, as temperature is increasing, it is resulting in phase changes. 3.3, in what phase is substance 1, that is a solid line, at negative 10 degrees Celsius? So if you look, negative 10 is between here and here, somewhere there, okay? So substance 1 at negative 10, that represents this part of the curve. And we know, we mentioned earlier, that substance 1 is a solid at negative 10. Just a solid. At what temperature does substance 2 melt? In other words, what is the melting point of substance 2? That is the dotted line. So remember the dotted line over here, we saw that substance 2 melts at that point over there. Now it's very difficult to see because this is obviously on a screen, and in an exam it'll be very clear and you'll be able to look at it very closely. But basically over there where I made the little red dot, that is the melting point. So you can see the graph was going up, it was inclined, that is solid phase. And then when it starts to flatten out, that's when melting is happening. That's melting. That's the phase change. So that dot over there, that is the melting point. And we've got negative 20 over here. So it's two little blocks down from negative 20. But you need to interpret your axes properly. So just because it's two little blocks down from negative 20 doesn't make it negative 22. Because if you look at your blocks, between 0 and 20, for example, we have 10 blocks. That means that every 5 blocks, that represents 10. Okay, so that means each block represents 2. That should make sense. So that is, for example, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's 10 blocks here representing between 0 and 20. So if between 0 and 20 we have 10 blocks, each block is 2 units, 2 degrees. So over here, that is 2 blocks under negative 20. So our melting point is negative 24 degrees Celsius. Because remember, each block represents 2 degrees. So negative 20, negative 22, negative 24 degrees Celsius. Please put your unit there because they ask for temperature. And temperature is not necessarily always measured in Celsius. We've got Kelvin, we've got Fahrenheit, and so on. 3.5 asks for boiling point, the definition. And grade 10's boiling point is one of the most important definitions that you're going to learn in grade 10 that will be tested in matric. So make a very, very important point in your book that this is a matric definition. We love asking this in matric. And I set matric papers, I mark matric papers so I know. So learn this one now in grade 10 and know it off by heart because it will be coming back in grade 11 and in grade 12. Now, very, very, very important for you to always mention temperature in your definition. Boiling point is the temperature of a liquid at which its vapor pressure is equal to the atmospheric pressure. You need to say it as is. If you don't, you will lose marks. Then 3.6, state the phase change that is taking place at B. B is over here, it's on the flat part of the graph. So when they say state the phase change, what I want you to do is I want you to tell me which phase is it in and which phase is it going to. So as we mentioned, this one is going from a liquid to gas phase. That is the phase change that is taking place. And just mention that that is called boiling or evaporation. So by mentioning both your covering or your bases, you're telling me the phase change is liquid to gas. That is exactly what the memo of this paper wants. But just mention that that process is called boiling or evaporation. Now 3.7 is a more difficult question. As you can see, it is 4 marks. So when you see a 4-mark question, you know you're going to be writing a mini paragraph for an answer. So it says the temperature remains constant at B. Yes, it does. The temperature does not change. It remains constant. Over there, you can see between 70 and 80 more or less. It says explain this phenomenon. In other words, explain why this is happening in terms of the spaces and the forces between the particles. So why is the temperature remaining constant? And they even tell you what they want you to mention in your answer. Don't ignore these prompts. You know that in your answer, they're going to give you marks for speaking about spaces. They're going to give you marks for speaking about forces. So first of all, if you need help understanding why the temperature doesn't change in these parts of the graph, and you need to go back and look on that theory, please go watch my previous video on the heating curves. But basically what happens is when a phase change is happening, heat is being added to the graph. So remember, from the start of the graph over here to the end, so from 0 seconds all the way here to 30 seconds or 40 seconds or wherever the experiment stops, we are adding heat. But it's not always going to cause a temperature increase. So sometimes the heat added to the substance won't cause the kinetic energy to increase, won't cause the temperature to increase, but that heat, that energy will be used to overcome the intermolecular forces, okay, to weaken, we don't say break intermolecular forces, to weaken the intermolecular forces. and that causes a phase change. So that is what we're going to be mentioning about forces. There's our 4 marks. The heat energy is being used to overcome or weaken, I guess you can say break, the forces between the particles. So remember, when they are liquid, they're packed closer together, those forces are stronger. But then we add heat energy, and at B, the temperature is not increasing because that heat energy is weakening the forces between the particles. That causes a phase change. The heat energy is not being used to increase the kinetic energy. That's why the kinetic energy stays the same, the temperature stays the same, but the spaces between the particles are increasing. So notice how I've mentioned both of these phrases that they've required. You need to memorize these so that when they ask you, why is the temperature constant during a phase change, or why is the temperature constant over here at the flat part of the graph, this is your explanation. 3.8 wants to know which substance has the weaker intermolecular forces between the molecules in the liquid phase. So if we look at the liquid phase of both of them, this is the liquid phase for B, and then we've got the liquid phase for A. So they want to know which one's particles have weaker forces between them. Remember, in the liquid phase, in the solid phase, the intermolecular forces are the forces that hold the particles together. Now, if you look at the melting points and the boiling point for both of these substances, we can see that in both cases, for B, the melting point and the boiling point is lower than for A. Now, as I've mentioned in the previous video, you need to know that the lower your melting and boiling points are, that is an indication that your intermolecular forces are weaker. It needs less energy in order to overcome those forces for the particles to go from solid to liquid and liquid to gas. So the lower the melting point, the lower the boiling point, the weaker the forces between those particles, because it means it needs less energy to change phase. Name the apparatus. So this is the piece of equipment in the lab used to measure the average kinetic energy of the particles. So remember, average kinetic energy of particles, that is basically your temperature of your particles. So think about it. What do we use to measure temperature? A thermometer. In this question, they give us melting and boiling points data in a table. Now, this is also linked to the kinetic molecular theory because they're speaking about melting points, boiling points, in other words, the temperature at which the phase changes start to take place, and we've got various substances. We don't see a curve, so this might make things a little bit more difficult to figure out, but let's see how it goes. Define the term boiling point. Remember, that is that very, very important definition that you need to know. From the table above, write down the letter A to D. So just the letter A, B, C, or D. So one of the substances that represents the substance which is a liquid at 100 degrees Celsius. So you guys need to understand that something that is a liquid at 100 degrees Celsius, 100 degrees Celsius will be before its boiling point. Because remember, if we have to draw a heating curve, that would be solid, that would be melting, that would be liquid, that would be boiling or evaporation, and that would be gas. Okay, you can fill those labels in as I said it, but basically this is solid, this is liquid, and this is gas. A substance will be liquid up until its boiling point. So I'm just going to call this BP, indicating boiling point, and its melting point will be over here. So basically, we're looking for a substance where 100 degrees Celsius is between its melting point and its boiling point. So where is 100 degrees between its melting point and its boiling point? And that would be substance D. And let's just see why. If its melting point is at 90, so if I had to write 90 here, but then it only boils again at 184, 100 would be somewhere over here, and it would be in its liquid phase. I hope that makes sense. The answer can't be B, for example, because do you see that substance B's melting point is at 133 degrees Celsius? So that means before its melting point. Okay, so any temperature before 133, including 100, it's going to be a solid. And through process of elimination, we can deduce that this answer is D. Then the next question says solid at 100 degrees Celsius. And we just discussed that B actually fits that description, because if you look at its melting point and its boiling point, its melting point is 133. Its boiling point is much higher, 444. If we want to look at 100 degrees, 100 is before 133. So 100 will be somewhere down here, and that would be when the substance is in solid phase. So solid at 100 degrees Celsius will be B. Then for C, they want to know which substance is a gas at 25 degrees Celsius. Now 25 degrees Celsius is quite a low temperature. And if something is in its gas phase, it means that the temperature has passed its boiling point. So basically we want to look for a boiling point that is below 25 degrees Celsius, if that makes sense. And the only substance that fits this description is C. And let's just double check if this makes sense. So I'm saying the melting point is -222 for C and -188 for C. We know that temperature is going to keep going up like this. So if that's -220, this is -118, up here will be -100, and then eventually we're going to get to the zeros, the 20 degree, 30 degree, and so on. So 25 would be up here, above its boiling point. And remember, after the boiling point, the substance is in its gas phase. So definitely the answer to that question would be C. 3.1.3 says, which one of the following diagrams represents particle arrangement of substance A? So that is in the table we are considering this substance over here at -120 degrees Celsius. Write down I, or triple I. So just so you know, I mean, I'm sure you know, this represents a substance in its solid phase because look how closely packed the particles are. It's got a very high density, it's arranged orderly. You can see there's a nice structure here. Not much movement can take place of the particles. They will vibrate in fixed positions. This would represent a liquid. You can see that it's intermediate. Particles move around more freely. They occupy the space, or they occupy the volume, but they take the shape of the container, and this would represent gas. So just by comparing them to one another, we can see that that's solid, liquid, and gas. So they want to know A at -120. So if you look at A's boiling point and melting point, if I have to fill it in on this graph, the melting point would be here, -117, and the boiling point would be 78. You just have to think carefully now. -120 is more negative than its melting point. So -117, if you think about this axis, this will go -117, then as we go down, it'll be -118, -119, -120. So -120 will be somewhere here. So -120 won't be between the melting point and the boiling point, which means it does not represent liquid. It definitely does not represent gas because the boiling point is only 78. So if the substance, if A was 80 degrees, 90 degrees, 100 degrees, then it would be gas. But in this case, -120 represents solid phase. So you will write I. So we've got a heating curve of a substance is shown below. We can see temperature on our y-axis. We can see time in minutes on our x-axis. That's very good. We know that this is exactly what a heating curve looks like. And we know that this first inclined part of the graph represents solid. This represents liquid phase. This represents gas phase. The flat parts are the phase changes. Remember, if you're still confused about this, you're going to have to go watch my previous video on the heating curve. Write down the physical state, so that means solid, liquid, or gas, of the substance at time 15 minutes. So now you look at your axes. I'm going to erase that. We know time is on the x-axis. So 15 minutes. Here's 0 minutes. Here's 5 minutes, 10 minutes, 15 minutes. So we look up at the graph at time 15 minutes. That will be somewhere over here. And we just mentioned that the second inclined part of the graph is where the substance is in its liquid phase. So you will write liquid. That's what they mean by physical state. If they say physical state or phase. What is the boiling point of the substance? So remember, where the graph flatlines or where it goes horizontal first, that's the melting point. They can also call it the freezing point if we go backwards and do the cooling curve. So that's the melting point. This is the boiling point, the second time when the graph starts to go flat. So you're going to have to read this very carefully off of the graph. So I'm going to zoom in so we can do that together. Now it's very important to understand how these axes work. So this gives us a very clear graph, very nice blocks. So we can see that it goes up in increments of 40. So every solid line is another 40 degrees. So we got 0, then 40, 80, 120, 160. So this gap over here represents a 40 degrees Celsius gap. But within that gap, I have 10 blocks. So I just counted. There's 10 blocks. So 40 degrees Celsius represents 10 blocks. That means that one block will represent what is 40 divided by 10. One block would represent 4 degrees Celsius. So what I mean by that is we can see that the boiling point is over here. It is 1, let me do some bunny hops, 1, 2, 3 blocks higher than 120 degrees. So if one block represents 4 degrees Celsius, 3 blocks will be, so this will be 124, 128, 132, 132 degrees Celsius. I hope that makes sense. If you keep going up in increments of 4, bunny hops of 4, you will eventually get to 160. But our boiling point is 1, 2, 3 bunny hops above 120, 124, 128, 132. There we go. So a lot of your physics and chemistry paper will be you interpreting graphs, how to read off of graphs, making sure you understand the axes correctly, and just make sure that if they ever ask you to draw a heating curve, that you give your heading, your graph a heading. So it'll be heating curve of a substance or temperature versus time for a certain substance. Right, over here I've zoomed in a little bit, so the graph is still there, but they want to know how will the average kinetic energy of the particles of the substance be affected between. And do you see how the instruction says here, write down only increase, decrease, or remains the same. So it's nice, we don't have to explain, but for the sake of this question, I will explain A, because they do ask me to explain B in the next question. Another thing, just remember that average kinetic energy of the particles, that is a reference to temperature. Always, always, always. So they're basically asking, how will the temperature of the substance be affected? So they say between 0 and 5 minutes. So here is the 0 and 5 minutes. And we know that on the inclined part of the graph like that, the temperature is actually increasing. We can see that because the temperature was 0 degrees Celsius. And then after 5 minutes, it increased all the way up there. Okay, remember, each little block is 4 degrees Celsius. So that'll be 32 degrees Celsius. So the temperature increased. So your answer here is increases. And the reason why it increases is because the heat energy added, so remember heat and energy, same concept, same thing. The heat energy in this case, the heat energy added to the substance results in the substance result in the temperature of the substance increasing. So we've got like a cold solid, then we've got a warmer and warmer and a warmer solid. It has not changed phase yet. So the heat energy is used to increase the average kinetic energy, therefore increase the temperature. Then you label your axes, so temperature, degrees Celsius, time in minutes, or whatever the investigation tells you. Then between T5 and T10 minutes, so between T5 and T10 minutes, that's right after the first section that we just spoke about, we can see that the graph is flat. Look at temperature. Temperature is constant over there. So the average kinetic energy of the particles will remain the same. Refer to the kinetic molecular theory to fully explain the answer to question 3.2.3. So let's do that. So remember, when the graph is flat, the heat energy is being used to weaken or overcome. I have seen some memos use the phrase break, but it's not strictly correct. But, you know, weaken or overcome the intermolecular forces between the particles. So in other words, the forces that hold the particles together. So if we've got a water molecule and a water molecule, these forces, this dotted line is what holds them together. So during this flat part of the graph, the energy weakens these forces. Okay, that results in a phase change. And imagine that if we weaken or overcome those dotted lines, so it's made weaker, basically getting rid of them, basically breaking them, for lack of a better way of saying it, then the particles move further apart from each other. But the kinetic energy of the particles stays the same. The temperature doesn't change. And remember, that might seem weird because we're adding heat, but the heat isn't used to increase the temperature. It's being used to weaken these forces, allowing the particles to move further apart. There we go. The heat or the energy is not used to increase kinetic energy and therefore not increase the temperature as well.